turn it over to Dr. Young.
All right, thank you. Yeah, thank you, Professor Godric, for the very nice introduction. Good morning, everyone. Yeah, speaking of Young, last time I give this type of seminar, well, I give this talk many times at different other places, but last time I gave a seminar to this audience, it was what, 10 years ago when I was really young. Yeah, I flew out here from Berkeley in 1998 when I was just about to finish my Ph.D. thesis work. As Professor Godric mentioned at the interview, I got to explain to him what is high Q, varactor, inductor, why it's so important, why phase noise is critical. And I also remember you asked me to forward my slides to you because there are some questions we just couldn't nail down within the half-an-hour time slot with you. Okay, so time flies. I'm here 10 years. And today, I would like to talk about some of the research work going on in my lab. The title of my seminar is Wireless Microsystem Research. And it is a very broad topic. So I'm going to, how I'm going to get rid of that thing. There's always some glitch, huh? Yeah. Oops. Okay, so I'm going to start off by focusing my research lab things. So my research lab is really focusing on integrate advanced sensors, actuators, and low power electronics at the system level to achieve autonomous sensing and wireless communication capability for a number of critical applications. What I mean by critical applications is where size, weight, power dissipation, limited access are very important or critical system design constraints. Now, moving to this slide, sort of give you a general sense of what type of activity going on in my research lab. On the left-hand side here, it shows a few pictures of micro machine sensors. For example, up there, we have a surface micro machine string gauge sensors that was fabricated by Professor Wang Ko, and I used this sensor to interface with electronics to build a wireless, batteryless string sensing element for mechanical rotating elements, such as sensing the string on a helicopter flying blades. And this is a top view of a silicon carbide capacitive pressure sensor that was fabricated in collaboration with Professor Chris Zorman. To achieve high temperature capacitive sensing capability, we demonstrate up to about 400 degrees C sensing capability that can be used for various high temperature engine, pressure sensing. And this is a picture of a silicon-based pressure sensor. Instead of using silicon carbide, we use a silicon-based pressure sensor. It's a very small area. It's about 0.5 millimeter by 0.5 millimeter size. And later on in my talk, I will talk about how we design and fabricate these sensors and use them for in vivo small animal implant to monitor the real-time physiological, biological information. And this is an accelerometer, a single-axis accelerometer designed by one of our master students. We didn't fabricate it using the case facility here, but we actually sent the layout to an external foundry to fabricate this device. Now, as you know, building sensors is very interesting, but if you want to build a useful microsystem, you need to have interface electronics. At the end, if you guys acting as customers, when I pass the device to you, you're putting on 3-volt battery. You ought to get some useful information out of that unit, Whether it's analog information or digital information, I don't really care. But those information ought to tell you what type of sensing element, what type of information you are sensing. So having interface electronics is very important. And these just shows, chips that designed, fabricated by my graduate students in my research lab used to interface with this type of electronics. And so combining the sensor and the low power interface electronics, we can take the microsystem for various applications. As I mentioned earlier, this is a string gauge sensing applications, high temperature pressure sensing applications, and we have a ongoing research project with the nearby VA hospital, and also in collaboration with Professor Steve Godric, by looking at how to implant a miniaturized wireless pressure sensor in the bladder okay, to sense the blood pressure for patients who suffer from urine incontinence. And my research task, right, in this case is to look at how we can use external radio frequency power to recharge an implantable battery inside the bladder. Okay. And also we have used this type of system to build implantable EMG sensor, right, for patients or soldiers who suffer from losing legs. So you can take you can try to measure the EMG signal from the residual muscle, and the wireless transmit out to a external receiver, and after signal processing, we can achieve much better control for artificial pylon or leg. There's another ongoing research project is to look at how to implant, well, not necessarily implant, how to place a small sensor, okay, at the bottom of a soldier shoe, and to measure the zero velocity and be able to transmit the zero velocity out to a handheld PDA. And we can use that information to constantly update the IMU, which consists of accelerometer, gyroscope, and if you do research in that area, you know that those devices suffer from drift. So if every step we make, we know when the velocity is, we can use that information to zero out the drift to achieve much better improved performance. And they also used it for various biomedical applications, for example, cochlear implant and a small animal genetically modified, genetically engineered mouse implant for various biological study. So today's talk, I only have about 55 minutes. I can't go through all of these examples, but I'm going to focus on two research examples on the small animal implant and the cochlear implant. So you get a feel what type of sensor we design, why we design it, what are the system issues, and what type of performance we can achieve. Because each talk can really get into a 2-3 hour discussion if you want to really get down to depth. Okay, so let's start talking about a wireless batteries implantable blood pressure sensing microsystem for real-time genetically engineered mice monitoring. So before we get into the engineering design, let's look at the biological motivation. Okay, so the biologists or people in biomedical research nowadays is asking a very important question: is what is the connection between a complex biological system that consists of DNA, RNA, various cellular network, to a list of questions shown on the right-hand side here, such as what is the genetic variation susceptibility to diseases? Okay, what is the gene functions? What is the biological pathways? And what is the disease origins? So by understanding these questions, hopefully we can come up with better treatment methods for similar human diseases, right? To block the biological pathway, okay, if we can understand the gene function and the disease origin as an effective method to suppress the disease development. And the approach people take nowadays is to use a genetically engineered mice, what's so-called a knockout mice, and to look at its long-term real-time multifunction signals, such as blood pressure, biopotential signals, temperature, core body temperature signals, and activities. And I, as an electrical engineer, my job is not to address the question at this level, right? My job is to develop a miniaturized sensor that can be implanted into the small animal and get all these signals come out in the real-time domain and provide those information to my collaborators, for example, people in genetics department or biological science department, to answer these questions, right? All right, so let's look at what is the commercial implant device available today. You can buy those implant devices. There are two companies in the US. One's called Data Science, the other one called Millimeter. You can buy these implant devices. And for example, this is the picture of a commercial implant that I didn't purchase. My collaborator at the genetics department purchased using his experiments. And we just got some devices and measured it and looked at what's going on inside. So this unit provides vital signal monitoring and data telemetry. For example, it allows you to measure heart rate, body temperature, and activities. But now, if you look at this design, okay, without opening this sort of a glass encapsulation, if you design integrated system, it's very clear to you, right? It is, I call it a discrete-based design. It has, PC boards, has many chips, resistor capacitors, and a large ferrite core. So by looking at this picture, you know that a discrete design will always lead to large form factor and a large power dissipation. Simple as that, you just need to burn a lot of current to drive the parasitic capacitance associated with the, on the board. And because the large power dissipation burned by this unit, we need to use a large ferrite core, coil, to receive the external radio frequency power to power up this device. So therefore, this large ferrite core is needed for the high system power dissipation. So overall, right, we end up with a large system size and a mass. Typically, if you weigh this device, it is about 2 grams. Now, 2 grams to us is small. I can carry hundreds of grams, right, without any problem. But however, for a genetically engineered mouse, it occupies about 15% of a mouse body weight. So this is an X-ray picture showing that if such device implant into the abdominal area of a mouse, the animal, if lucky enough, survive from the surgery, and you can measure various biological signals. But however, the animal definitely suffers what we call a post-implant trauma, and therefore the biological signal that you get, for example, you get the blood pressure, you get the heart rate, these are highly distorted signals. Right? For example, if you use a football-sized implant put in my body, I may not die. I can give you my heart rate, my body temperature, but these are highly distorted, right? It's not the correct biological information under my normal state. So it's very important, right, to build something very small to be implanted into the animal so that you don't disturb its sort of a normal operating condition. So let's look at how we can build this type of implantable system. So this is a general system architecture here, So we have a microfabricated sensor array. Some of them are micro machine fabricated. Some of them are just using conventional microfabrication technology. Some of them can be microfabricated by using CMOS transistor technologies. So they consist of temperature, biopotential activity, blood pressure, and later on we plan to add on some chemical sensors. So on the right-hand side, and this is a system diagram for our integrated circuits design. And you can see there, right, it consists of interface electronics because all these sensors need to have some interface electronics to convert the sensor output, whether it's capacitance output, resistance output, or voltage output, into some electrical signal and a multiplexing going through analog to digital conversion. And at this point, we get digitized information, we transmit it to the external receiver. And the chip also contains of adaptive radio frequency to DC power conversion. I'll talk about this adaptive stuff later on a little bit more. So take a radio frequency energy comes in, convert to a DC on-chip supply. This is a 2 volt and with few hundred microampere current driving capability to run the whole system. And of course, we have extraction unit to run the digital logic to run the system. So from this picture, you can see that, right? It is an integrated system design. Therefore, we expect to achieve low power dissipation, and I'll show you the power dissipation is very low, and from the measurement results. And because of low power dissipation, it allows me to use a small powering coil to receive external energy, to power the system. It is a miniature form factor, lightweight, and we can achieve multi-channel sensing simultaneously in a real-time domain. And after the whole thing is built, it is a standalone wireless biosensing microsystem. And the picture down here just shows that you have this type of unit put into a genetically engineered mouse that can run around inside a cage without having any wire attached to it. From this picture, for illustration purpose, I showed that we have a coil that's built at the bottom of the cage that's used to transmit a radio frequency power to the implant unit. And we have another coil placed on top of the cage that gets the data. But in reality, this coil can be placed anywhere as long as it can receive the data. But for the illustration, I have 2 coils positioned on top and the bottom cages to show you that we do have 2 separate antennas. One for the power goes in there, the other one gets the data output. Now, the important thing here for this talk, right, is I'm going to emphasize on the blood pressure. And I don't have the time to talk about the temperature, biopotential, activity. Let's focus on the blood pressure. And so this is the blood pressure continuous time domain waveform we want to achieve. All right, so talking about the blood pressure measurement, right, the first thing we ask is, I always ask my graduate student ask the question, right, what can be done nowadays? What's the typical approach? Now, one approach is to use a catheter tip transducer. This is the catheter tip transducer. And with a dimension on the order of millimeter size, that you can break the vessel and insert the cathode tip inside the vessel. So the disadvantage is it's an invasive approach. It requires rather complex implant procedures. And at the tip of the vessel, at the tip of this cathode tip, there is a pressure sensor in there, and it has wires going out there to interface with the circuits, get an electrical signal representing the pressure information. But however, this type of device, commercial available device, suffer from sensitivity degradation and a drift over time. And because the vessel occlusion, right, you can cause potential blood clogging and all that can really make the animal, cause the death to the animal. And these animals are quite expensive. It's not the typical, mouse that runs around, right? In your basement, these are genetically engineered. You go through various string selection breeding process to get animal that possess the genetic sequence or profile that you want to have. Another approach is to use tail cuff device. Tail cuff device is relatively easy. You take the animal, you shove that into this tubing. Okay, the tail comes out, right? And you got this cuff that enclosed around the tail that you can get systolic and diastolic blood pressure. You get the highest pressure point and the minimum pressure point. The problem here is, well, this is like what you do when you go to a doctor's office, right? They got this cuff around your arm to measure pressure. Sure, we don't get nervous when we go to the doctor's office just to measure the blood pressure. But if you shove this animal inside this tubing, right, having the tail come out, it gets stressed out. It just doesn't know what you're going to do right? And of course, the blood pressure may not be accurate, okay? So what we plan to do, right, now you can see that what we plan to do is we want to build a less invasive blood pressure monitoring system. And a less invasive, that doesn't mean that you don't do the surgery. We still have to do the surgery, but we want to implement a cuff that goes around a blood vessel, okay, without breaking the blood vessel. This picture just shows this is the original concept, right? My collaborator, Professor Wenko, come up with this concept, say that, well, if you can build this type of cuff around it, and the blood pressure inside this vessel, okay, expands and contracts, okay? So the blood pressure can be coupled to the cuff due to the expansion and the contraction of the vessel. Now, inside this cuff, okay, and we have, pressure sensors, low power integrated electronics, and to sense the blood pressure and be able to transmit the data wirelessly to the external receiving unit, and the external coil can also couple the power in. So what we're measuring here, due to the expansion and the contraction coupling the pressure from the vessel to the cuff, what we're measuring here is a downscale version of the blood pressure. So that typically, from our various implant trial, we know that we're getting about 10%. So instead of getting the full data, we're getting 10% of data. Signal is much smaller. So if you design electronic system, right, the first thing tells you, wow, this is not a good news because my signal becomes much smaller. What that means is to achieve the same resolution or number of bits, right, my noise level needs to be much smaller, okay? And if you want to get the low noise, what do? If you take, EECS 246, right, it tells you that you need to burn more DC power. So the power have to go up, and that is not desirable for low power dissipation. So you have to do a very sophisticated electronics design to make sure that given the 10% signal degradation, you still can achieve the required resolution and you still can do the low power design. And I'll talk about this later on in my talk. Okay. What else? Okay, in this configuration, we're avoiding the vessel penetration and the blood clogging. And also, right, because this cuff is built using elastic materials such as silicone, we can minimizing the restrictive effect of the blood vessel. Just imagine, right, if you have a cuff goes around your arm, and if the cuff applies large, high pressure to your arm, and if it leaves the arm for 10, 15 minutes or so, right, you don't feel comfortable, and you can develop, okay, sort of hypertension locally. So the cuff needs to build using elastic material loosely coupled, okay, to the vessel, so that you don't apply too much pressure on it. But the loosely coupled the configuration also results in a reduced signal coupling. If it's very tight, right? It's very tight. You get a large amount of signal coupling, but it's not good for the local pressure. If it's loosely coupled, the story turns around. Okay, so now. My graduate student Pen Kang spent years, develop this type of cuff. And also the implantable electronics, we built a circular cuff as I showed earlier. It turns out that circular cuffs works. It only works for large animal with relatively large vessel diameter on the order of millimeter or 2 millimeter. But for small animals such as genetically engineered mouse, the vessel diameter is only about a 0.2 or 0.3 millimeter. So the circular cuff couldn't be used effectively to measure the blood pressure. So here I show a 2D, okay, blood pressure monitoring system. As you can see this configuration, right, it is not a circular design. It is a flat design, okay, it's a flat cuff design. So this is the latest version that we developed just to interface with small animals such as mouse, okay. So what do we have here? Let me try to explain that to you. So first of all, you know, we have a flat structure instead of a circular cuff to interface with a small vessel with a diameter about 0.3 millimeter. It's very little tiny. 0.3 millimeter is, 300 micron, right? You all know the millimeter size by looking at your ruler, and it just divides by a factor of 3. You get a feel how small the vessel is. So what's important here is that down here I have a thin silicone membrane. In silicone membrane, encapsulating a cavity area that filled up with insulating fluid, such as silicone oil. Okay, that's very important. Now, underneath this cavity, we have a MEMS called micro-electromechanical system pressure sensor, such as a diaphragm, that is directly sitting on top of an integrated circuit chip, an IC chip, that has an area about 2 millimeter by 2 millimeter. And the electrical connections is formed by wire bonding from the MEMS to the IC, right, and the IC to the substrate. So if you have this device directly drop on top of the IC, and later on in my talk, I have a better process flow to show exactly how that's done. And as the vessel expands and contracts, it couples the pressure, right, from this thin membrane, which you can call it a sensing membrane or coupling membrane, through the fluid, okay, the fluid to the silicon membrane, okay, on this MEMS sensor. Now on top, okay, we have another structure that covers this this vessel, and inside the top flat structures, we use a stainless sheet. It's a very thin sheet, about 75 micron or so, okay, encapsulated in the top layer that is used to prevent any external environment variation from coupled the external disturbance signal to the vessel, such as the muscle moves also, right? If this is a soft material, it will couple the external variation or pressure information to the vessel, so you're getting some additional information you can't really calibrate out, okay? And we use a thin wire, okay, a 150 micron wire, a diameter wire, as a clamp to clamp the device. So you noticed here, right? There is an opening, okay? There's an opening. So this opening in the surgery, you actually open this up and slide the vessel in there, close the opening and put a clamp on it to secure the relative position of the vessel to this cuff device. Okay, so this is the fabrication process. I'm going to quickly go over there. Okay, so basically we use traditional conventional machining process to build the mold. We have mold A, mold B, mold C, right? And using biosilicone material to fill the mold after you go through the degassing, curing process. And of course, you need to apply a glass substrate, okay, on top of this mold with the weight applied to achieve a uniform thickness. So you get these 3 pieces from this traditional machining process, and you peel that 3 pieces out of the mold, and you can glue them together, okay, using adhesive material to form the cuff. So I got a part C here, right, and the part B and the part A. I glue them, and this is the opening where I can really open this to slide the vessel in there. After that process, I introduce another sort of, I call it base carrier. I have a flexible PCB. I got the my IC chip here, got a MEMS sensor on top, and a wire bonded and coated by using silicone coating. And over the flexible substrate, I have IF coils, okay, that for the powering. And I also have a few discrete components such as capacitors for tuning the RF coil. And all these things, so those capacitors can be implemented as part of the chip. It just gets the chip area relatively large. So if I can leverage the coil size, right, because the coil already occupies this dimension. If you drop a few capacitors at the middle of the coil, it does not really consume additional system area. So now, right, I'm going to attach the silicon sensor piece on top of the IC and the MEMS and the IC module. Puts the clamp on it and fill this middle area by this yellow color representing the silicon oil. It is sort of, you can call it a transmission fluid, right? That needed to transmit the pressure that is going through this thin membrane to the fluid down to the membrane of the capacitor pressure sensor. So this is a picture of a final fabricated device. I'm very proud that my graduate student Pencom puts a lot of effort in to finally get these things together. It looks simple, but takes a huge amount of engineering labor, right, to get this done. So you can see that this is the radio frequency coil that's needed to get the power in. And these are the traces. This is the chip, 2 millimeter by 2 millimeter chip with a MEMS pressure sensor somewhere in there. You can't really see it because you got this silicone cuff sits on top. And this is the 150 micron diameter wire used as a clamp. And this is a thin wire that going through the middle of the sensing cuff, sort of mimicking a blood vessel. In reality, right, this wire would be a blood vessel that you use this sensing cuff, flat sensing cuff to enclose around the vessel for blood pressure sensing. And the total weight is only 130 milligram, right? That is 15 times smaller than the conventional weight, right? I showed you earlier, that's about 2 grams, okay? So it's about 10x, more than 10x mass reduction compared to any available implant technology today. Okay, so now I'm going to talk about subcomponents. Sort of up to this point, I provide you a big picture, right? What is the motivation? How we can use silicone cuff to sense the blood pressure. A very simple first order fabrication process flow to show you what the whole thing looks like at the end. So now I'm going to go down one level down to the device level. So let's look at the MEMS capacitor pressure sensor. And we use MEMS capacitor pressure sensor. Well, before I talk about this, I want to tell you that a capacitor pressure sensor consists of a edge clamped silicon diaphragm. This could be a circular structure, or could be a square structure. But in our design, we use a circular structure. And edge clamped underneath, for example, a vacuum cavity. Now, when you have external pressure applied on top of this membrane deflects down so that you can get a variable capacitance. And if you plot the capacitance versus pressure area, right? So below the touch point pressure, before the capacitance touch, right, the relationship is, on the first order, is 1 over the gap size, right? So you get this sort of a nonlinear capacitance behavior. After touch point pressure, okay, so the touch area start to increase, and then you get a nearly constant, okay, capacitance change versus the pressure change, okay? And Professor Wenko and his Ph.D. student, Dr. Wang, published a well-written journal paper, right, Sensor Actuator, back in 1999, based upon Wang's Ph.D. thesis on this touch mode capacitor pressure sensor design fabrication. Now, if you're interested in learning this device, I suggest you read this paper. It tells you pretty much everything you need about how to design the device and the fabrication process to fabricate the device. So we picked pressure sensor. It has 0 power dissipation, 0 DC power dissipation. That's very important for low power design. And it has a very low temperature dependence and turn-on drift. Has good time stability. And it can be optimized design for dynamic range, sensitivity, linearity, and size. And these information are all well presented in this reference paper. And from the circuit's perspective, okay, I like capacitor because capacitor allows me to easily design switch capacitor-based interface electronics. Okay, before I come here, I delete the 2 page on the fabrication process because the time constraint. but I'm going to just show you that after going through the MEMS fabrication process, that definitely can be done. A lot of paper written, from the results fabricated at the MFL on the third floor Bingham. So this is the SEM picture of the pressure sensor. It's about, you can see that it's about less than 0.5 millimeter by 0.5 millimeter by 0.5 millimeter size. If you take a scissor, right, or if you take a dicing saw to cut through this device at the middle, and then you look at the cross section, what do you see? This is what you see. You see a silicon diaphragm. It's about 2 micron thickness, suspended with an air gap on the order of 1 to maybe 1.5 micron. Of course, right, once you break it, the pressure, right, is equal, right, top and the bottom. So this diaphragm is flat. If you had a vacuum underneath, this diaphragm will bending downward, okay? So as you apply additional pressure, this diaphragm will further deflect towards the substrate to get a capacitance increase. So this is the sensor measurement results. This is just one of the typical measurement data. I don't bother to show a family of curves that we measure. It shows that we can get a nominal capacitance value about 1.8 puff at the 760 millimeter mercury height. That's 1 atmosphere pressure. And the sensitivity, okay, is at this point is about 1 femtofarad capacitance change per millimeter mercury height. And this sensitivity can be further improved if you can design a better sensor. But given the sensor we have, I can't do too much because I have to design my electronics to work with the device. Right? You either design a sensor that's good enough, design your circuits, work with it, or you say, forget about the circuits, let's go back to the MFL again to fabricate a better sensor. So my decision back then was, let's take this sensitivity, move on to the next stage. So let's talk about the integrated electronics design system. So this is a complicated picture, but I'm going to spend a few minutes to explain that to you. So this is the design architecture, okay? Let's start off outside. We have an external class E power amplifier, and there are well-established equations in the textbook for you to tune the L's and the C's. Some of you in this room are the expert now, right? Can be much better than me in tuning these things. So this thing generates a radio frequency power, gets coupled to a LC network, okay? So small L and a C's. That is a part of the implantable system. So the radio frequency power by the inductor coupling and at the 4 megahertz goes inside the implant system. Why choosing 4 megahertz? You just have to believe me. We have done extensive lab bench calibration to show that for the given geometry that we pick, 4 megahertz is the optimal frequency. If you change your geometry, may become 3, may become 10. Okay? So for us, it's a 4. So the RF voltage comes in. We go through a DC. We go through a CMOS voltage doubler to generate the DC voltage high and the DC voltage low, 4.5 volt and a 2.5 volt. And these will drive, I call it drive a array of on-chip voltage generators. And you notice that we generate separate 2 volt supplies for the analog and the digital circuits. This is 2 volt analog and this is a 2 volt digital, because we want to minimize the coupling, okay, from the digital circuits to the analog circuits. And we have an interface electronic circuits and the CV converter that converts the capacitance, right? Because the MEMS capacitor pressure sensor can be modeled as a capacitor to the analog voltage, okay? And we use 11-bit ADC to digitize this information. And we use a 1-bit, okay, integrated power sensor with wireless feedback, okay, to adaptively control the external power source to make sure that, right, when the animal moves around inside the cage with different position and the tilting angles, the magnetic field coupling varies a lot. We want to make sure that we get a stable power supply to power up this microsystem. And we use frequency shift keying, okay, at the 433 megahertz modulator to transmit the digital blood pressure information along with this 1-bit power sensing to the external receiver. So the external receiver gets the digital information and also gets the power level. And it depends on the 0 and the 1-bit pattern of the power level. It will adjust the supply voltage here accordingly to make sure that, right, the implant gets the adequate amount of power supply. Wow, got 25 minutes left over. So this is the interface CV converter. Due to the time constraint, I won't get into detail to talk about how to design this MEMS capacitor pressure sensor. And basically, this is a very sophisticated design, low power, and achieve the dynamic range requirements. And if you want to know more about this, Pencon had a CICC paper published September last year. So you can read about this paper, tells you sort of first order what you need to design a system like this. Okay? Now I want to spend maybe just 1 minute talk about this adaptive RF powering. And because only 1 minute, I can't get into a lot of detail. My graduate student, Natapong, also had a IEEE sensor paper published October last year to describe the detail how the adaptive powering works. Is when the animal, for example, when the animal is at the stationary, it's not moving, okay? You had a constant coupling factor. So the power that coupled to the implant device is pretty much a constant if you look at this average. So if you look at the 1-bit power data, it's a 50% duty cycle. Now, if the animal all of a sudden stands up or moves to a region where the power coupling coefficient K drops, so this will produce a lot of zeros, let's say that in this case, right? And a lot of zeros sent to the external unit. The external units will notice that the power is very low now. It will start cranking up the external power, okay, to power up the implant device. So the implant receives the power also cranks up until it gets to this nominally defined threshold. Then becomes 50% duty cycle again. So when the animal moves to a high coupling region, right, the opposite occurs. So that's how you use that system to tracking the animal movement and adjust the external power supply to get a constant supply voltage for the implant. So this is a fabricated chip micrograph, and it's done in a 1.5 CMOS process, 2 poly to metal process. It's a very cheap process, 2 millimeter by 2 millimeter area. Only cost us back then was $1,000 to fabricate, one chip like this. And the whole system consumes 120 or 150 microampere from a 2-volt supply. So this is equivalent to a 300 microvolt, okay, power dissipation to run the entire system. So sort of refresh your mind again, right? And I got a chip here, and I got a MEMS pressure sensor that I showed you earlier. The sensor is on top of the chip, wire bonded to form the electrical connection, and puts on this carrier substrate containing, discrete components for tuning, for transmission, and with bond wire coated with a silicone coating and encapsulated with this sensing unit, and where the blood vessel is inserted at the middle of the structure during implant. So let's look at some of the system characterization, and we characterize the ADC alone. There's an analog to digital converter because you look at digital bits. You want to make sure that the ADC really hits the performance specification. If something goes wrong after that, it must be the front end, right? Otherwise, you have several building blocks connected together. You just can't figure out where goes wrong. So the ADC meets our performance, 65 dB dynamic range. And when you connect the ADC with the front end CV converter with the capacitive pressure sensor, without applying any signal, all of a sudden the noise goes up because the CV converter introduced noise. So the total noise is equivalent to 75 attofarad, which is equivalent to 0.1 millimeter mercury high resolution, corresponding to a 60 dB dynamic range, which is about what we designed for a 10-bit resolution. So this is the output digital code, right, out of the ADC, and versus the pressure change. Okay, if we sweep the pressure, okay, from 760 to about 960, and this is the digital code. Tells us that our average sensitivity is about 8 LSB, and with nonlinearity and a hysteresis less than 2.5 and a 1% full scale. Now, okay, so this is the implant test, right? We have a mouse that go through the implant process, and this is the the implant picture. You got this aorta artery going through the center region of the cuff, right? This is the RF powering coil. This is my chip. My pressure sensor is right at the middle, right? Sort of encapsulated by this cavity filled with silicone oil. I have my external power amplifier with adaptive voltage control, right? I can send the power in, and I also can get the digital data out. Okay. And tells you that this is the wirelessly received blood pressure data. This is done during the implant. This is done after the implant. Measurement from mouse freely moving in its own cage after recover from the implant. So during the implant, the digital code varies from 715 to 760. Tells us that we get a 60 millimeter mercury high resolution. The heart rate is about 450. So assuming a vessel pressure variation range about 40 millimeter mercury high, because we have done a lot of those tests previously, know that this is about 40 millimeter mercury high. So it tells us that our scaling factor is pretty much close to what we wanted, 0.13, and we expect a 0.1. Okay, so post-implant, the vessel pressure range is about 31 millimeter mercury high. Heartbeat goes up to about 520. So it tells us that, you know, the blood pressure amplitude drop a little bit. Likely is due to the weakened heart condition. And you also see that, right, the amplitude variation is much reduced after the implant, during the implant. This can be caused by a balanced tissue support, because when you do the implant, right, one side is open, underneath you have the tissue, but when you close up, you have the tissue on top and the bottom. So it's much less it's much less susceptible to the external sort of muscle movement to cause this type of amplitude variation. And we do notice that the noise gets a little bit higher after careful characterization. We notice that the noise is about 3 dB higher after the implant, you know, after animal gets recovered. This is likely due to the vapor penetration. Okay, going through the silicone cuff cause this noise enhancement. Due to the time limitation, I won't show you this, you know, a movie. Just tells you that, you know, when the animal moves inside the cage, you know, the waveform changes. Okay, adaptive powering. So now, because I got 15 minutes over, I need to talk about the second part of the story, which is MEMS middle ear acoustic sensor for fully implantable cochlear prosthesis. I'll talk about the accelerometer that we designed, fabricated externally, the interface electronics designed in our lab and fabricated by Moses, and how we can combine these two pieces together, put it into the middle ear as a implantable acoustic sensor for fully implantable cochlear prosthesis. So before I get started, I'll talk about the research motivation, why we do this. Okay? And more than 30 million Americans, including 4 million children, suffer from conductive or sensory neural hearing loss. If you want to understand, right, if you want to understand what is sensory neural hearing loss, you need to know how our, you know, sort of hearing system works. So here I shows a picture of our sort of ear structure. Acoustic pressure information comes in going through the ear canal and modulates this sort of a layer of tissue we call the eardrum, or we also call the tympanic membrane. So the tympanic membrane displacement will cause movement of the articular chain, which consists of malleus, incus, and a stapes. The stapes, right, will pushes the cochlea to couple the mechanical energy into the cochlea. The cochlea is, let's look at what's inside the cochlea, right? So this is the cochlear structure. It's a spiral biological sort of a tube structure. If you take a scissor or a knife to cut through the cochlea, what you see is a cross section, okay, consisting of, you know, a number of biological chambers, okay, with a typical dimension on the order of 1.5 millimeter. And if you look at this region here, okay, there is a membrane that separates the top chamber and the bottom chamber. The top chamber is called a scala media. The bottom is called a scala tympani. And this membrane consists of, again, very sophisticated biological cell structures. To simplify this membrane, I tell you, this is what we call the basal membrane. You can imagine this is the base membrane. And this membrane here is what we call the tectorial membrane. It serves as a top cap, okay? So as I said earlier, right, when the stapes pushes due to the sound coming through the ear canal, it couples the mechanical energy inside the cochlea. But the cochlea is full with biological fluids. So again, you use the biologic, sort of use the fluid as a transmission fluid to couple the energy, okay, to couple the energy caused into the cochlea as a standing wave travel inside the cochlea, so that the basal membrane will vibrate up and down, okay? And the basal membrane has certain tuning characteristics. For example, certain position of the basal membrane only sensitive to 1 kilohertz, just like when you place the piano, right? At the keystroke, you have certain notes. Certain correspond to higher frequency, certain position correspond to lower frequency. So let's say that a particular frequency hits this tuned region. The basal membrane vibrates up and down. And it causes a deflection of the hair cell. So there is a mechanical deflection of the hair cell that triggers a potassium ion release that causes the neurotransmitter to be fired going through the nerve system, going to the brain. That's how you perceive the sound. So it's a cascade of mechanical, chemical, electrical sort of a stimulation. Now, most people who suffer from sensory neural hearing loss is the hair cell gone. The hair cell gone is due to, you know, for example, use chemical drugs or natural birth defects, or you exposed to very loud sound. Okay, if you expose very loud sound, the hair cell can get damaged. And one particular sort of a feature of this type of hair cell is if it gets damaged, it cannot be regenerated. They are gone, they are gone. So people develop cochlear implants, and basically what it does is that it has a external, well, in this picture, right, it shows that it has two coils. One is outside the head, right? The other one is implanted underneath the skin with a separation distance on the order about 5 to 8 millimeter. And this number 5 basically is a magnet. Okay, make sure that the thing does not fall apart, right? It's positioned alignment with the implantable subcutaneous coil. And there is a microphone that you wear behind the ear that picks the sound, and the microphone gets the sound going through the speech processing processor, outputs the processor data, digitally transmitted. Again, if you look at these two coils, right, just like two coils separated by a short distance, you can use the magnetic coupling to transmit external coded information to the internal coil, and the internal coil has a driver circuits that will drive the code, right, receive the digital information to this cochlear wire that insert inside the cochlear. And you can see that there's an array of electrostimulation pads on the order of about 8 millimeter. It's about millimeter by a millimeter size. Okay, array of electrodes to stimulate the nerve. So the system works. However, there are a few existing concerns. Now, for adults, it presents a social perception of being handicapped. A lot of people don't want to wear that. And for kids and the teenagers, right, it's extremely inconvenient for them to wear this type of devices. In particular, they're very active in sports and various water activities. But now, if you look at the entire system, all these systems can be potentially fully implantable. Okay? And people have shown that external speech processor can be designed as implantable speech processors. And this electrostimulation wire is already implantable because you have to implant anyway, okay? So the challenge here is to design an implantable microphone, okay? Implantable microphone is the challenge. How can we take this microphone that you wear externally and to design something that works and to be able to totally implant it inside the middle ear? So the proposed system picture is that, well, this is a, old drawing that I borrowed from Dr. Ko, probably was drawn maybe 25 years ago, right? So back then, you don't use PowerPoint, you use hand drawing, a lot of, artistic skill required. But anyway, okay, so what we want to do here is, right, we want to build a middle ear acoustic sensor, okay? And this is the ear canal, and this is the tympanic membrane, we call it the eardrum, and this is the bone, okay, inside the middle ear. Basically, we want to take a micro-electromechanical accelerometer, position the accelerometer on the temporal bone to detect the bone vibration, okay? So if the bone vibrates, and if this sensor can detect the bone vibration, and if the bone vibration information really presents the speech information, because it's the acoustic energy that modulates the tympanic membrane, causing the displacement, right, or vibration of the bone. And because we're using accelerometer, it can be fully packaged, encapsulated. We will expect a long-term implant reliability. Now, the conventional microphone, right, suffers from tissue encapsulation, a gross encapsulation that will cause, over time, it will have drift and also sensitivity degradation because you will have a hole, okay, to expose the outside environment to couple the pressure in, and the hole may have tissue growth on it. And the PZT-based, okay, piezoelectrical-based microphone suffer from environment noise coupling, and if you implant under the ear canal, it can cause sort of ear canal skin infection because this region is a very thin skin. So the microphone technique that we choose to take, right, can achieve expected long-term implant reliability. Now, let's look at human temporal bone micromechanical vibration characteristics. So before you design the sensor, you have to characterize the bone. Otherwise, you have no clue what type of sensor you need to design. Okay? So this is from literature, we know that, okay, the Umbo, so at the bottom portion of this, exhibits the largest vibration response, okay, in responding to the external acoustic pressure. That's what we already know. And there are because this bone vibrates from, sort of with a rocking motion, has multiple directions. So in this talk, I'm going to focus on the Umbo primary axis. This is a direction perpendicular to the surface. We also have done a secondary axis, which is in plane. But due to the time constraint, I won't share with you, all the data. So I'm going to just tell you what's going on with the primary axis. We take single tones going from 250 hertz to 10 kilohertz in between 70 dB and 100 dB SPL. So this is the dB unit, right, representing the sound pressure level. And we use an optical method using laser Doppler vibrometer to measure the volume vibration. So this is the setup, right? We actually use a sort of a cadaver bone, okay, cut from half of the head. It was scary, but I had the graduate student, very good, Mark Zorcher, was brave enough to wear the glove, go to medical school, to manipulate with their pieces, and using laser vibrometer to measure the vibration characteristics. Okay, so this is the umbo, and you notice that he puts a thin aluminum foil at the umbo, so enhance the reflector beam, so that the reflector signal will improve the signal-to-noise ratio. You can get reliable data. So this is the setup. The important thing here is this is the measurement results. The displacement versus frequency, and at a different sound level. You notice that it exhibits low-pass filter response with a corner frequency about kilohertz. If you plot the displacement versus the input sound level, it exhibits about 20 dB per decade characteristics. Okay? So that data, we measured it. It matches with existing published data from other research groups, such as the ones from Stanford. So give us sort of first-order comfort, right? We have done something right, and we can have some minimum confidence on our own measured data and use that to derive the design guideline for the accelerometer. So next thing is, right, well, what I showed you earlier is the displacement. And earlier I said that I need to build an accelerometer. Okay, so I'm not building a displacement sensor, right? I'm building an acceleration sensor. So I need to convert the displacement to acceleration. So this is the converted data, right? Tells you that acceleration increase with omega square, okay, because you differentiate it twice, right? Once to velocity, second time to acceleration. So it goes up by omega square 40 dB per decade up to 1 kilohertz, and have a reduced slope about 20 dB per decade up to 4 kilohertz. One thing you notice that is that because of the omega square, the larger acceleration, we get a larger acceleration at higher frequencies, okay? For the same amount of vibration amplitude coming in, if it's at a higher frequency, it will result in a higher acceleration. So it tells us that, right, for the worst design, we actually need to design for the low frequency. If we can detect the low frequency vibration information, which results in a reduced net acceleration, then at high frequency, life becomes much simpler. Of course, this shows the linear characteristics. But what we need to, also we know that it's about, slope is about 20 dB per decade. What we need to measure is what is the normal sound conversation. I'm talking very loud here. So I think I'm producing maybe 75 dB SPL. But if you sit back there, what you're hearing, maybe it's about 60 dB SPL sound. Okay, so what I consider this is normal conversation. So if you extrapolate this data, okay, this is the 500 hertz low frequency data, and my measurement only go down to about 70 dB SPL. So I need to use this dotted line along 20 dB per decade to hit to this value. It tells me that if I want to measure 60 dB SPL sound at 500 hertz, I need to be able to sense 1.5 millig. Okay, that is very important information. We have spent like a year training the students, deriving the data. Why we do this? We want to come to this plot. This tells us our design requirements. So the Cochlear electrode, okay, exhibit about a 200 hertz bandwidth at about low frequency end. Okay, sort of this is just like an array of bandpass filter, right? And each one has certain bandwidth. At the low frequency, about 200 hertz. So you do a simple calculation, say that 1.5 millig, 200 hertz bandwidth. If you need to know the noise spectrum density, it must be 75 microG per root hertz. Okay, and for reasonable sound recognition, we need to have a sensor with a bandwidth of about 8 kilohertz. And from the previous measurement, we know that the maximum acceleration we get is about 10 G, and the packaged mass size, Professor Cole has done a lot of existing work, tells us that the whole thing needs to be packaged less than 20 milligram, so that you don't provide additional mechanical loading or damping on the bone. Right? If the device is too big, the bone just does not vibrate as much, so you're getting an out of the frequency sort of a response. So these are our design requirements. So now how we design the MEMS accelerometer And I won't tell you how to design it. Basically tell you this is the MEMS accelerometer pictures, right? Tells you that you got to interdigitate the finger structures. When the acceleration comes, mass will move from one way, so the gap size change, the capacitance change, so you get the CS plus, CS minus, get a differential design. And all the good things that I talk about, the capacitive pressure sensor, right? The capacitive device applies to the capacitive accelerometer, low power, low turn-on drift, blah, 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 all applies here. So one thing I want to talk about here is, when you design sensor, this type of sensor has its own noise limitation. We call it Brownian noise. Is you have a suspended mass supported by the mechanical spring. Under room temperature, the mass vibrates. Even if the whole thing is positioned on a vibration isolation table, the mass vibrates. So if the mass vibrates due to the thermodynamics, you don't know whether the vibration signal is due to the acceleration or the noise. But the good thing is there is a simple formula to predict the noise spectral density. Okay, we call it Brownian motion. Is 4 kT times the resonant frequency divided by mass divided by the Q. And this is our design requirements. You plug in there, it tells us that we need to have a minimum mass about 2.5 microgram. Below that, noise higher. Above this mass, denominator goes up, the whole value goes down. So we designed our system, sort of a 1 millimeter by 1 millimeter size. We can pack 189 sets of fingers. We get 18 microgram. That's good. The mass is bigger than what we needed. So we expect to achieve a 28 microgram per micro-G per root hertz noise floor. Okay, so this is the sensor electronics. We use a synchronized detection circuit, minimize 1/f noise. The whole system is designed to achieve 25 micro-G per root hertz. And the detailed reference paper, right, is published in this IEEE JMM journal. If you're interested, you can read about it. It tells you everything you pretty much need to know to design a chip like this. Okay, so this is the SEM picture fabricated by the external foundry, right? This is the finger, the movable fingers. So we have the sensor here, the IC here. Well, this is a 2 millimeter by 2 millimeter IC. What's inside this red box is electronics that you need to convert the accelerometer output to an analog voltage. Wire bonded and exhibits a 4 finger fail per G, and with a dimension about 2.5 millimeter by 6.2 millimeter. So the whole thing weighs about 25 milligram, which is a little bit higher than the 20 milligram requirement, but we still go ahead to do some implant study. So I want to show you some noise spectrum density. Basically tells you that this is the noise floor in ambient, and this is noise floor putting the vacuum when we're trying to lower down the Brownian noise. And then we do see a tone. This is the mechanical resonance at about 6.44 kilohertz. Tells us that our resonant frequency is 6.44 kilohertz, while we design is about 8 kilohertz, but there are some discrepancies due to fabrication imperfection. And also in this design, the electronic noise dominates the whole noise floor. So this is the implant characterization, right? We put this device sort of, we don't have the package to cover the top. This device is put on the bone. Actually, the bone is right here. This is where you're looking into your ear canal from inside your middle ear, okay? So the sound is coming from the back side of this screen, right? So this eardrum will vibrate, and the bone will vibrate up and down like this. So this is the sensing axis. So if my output analog voltage derived based upon the accelerometer output, if everything works right according to the signal processing concept I illustrated earlier, if I take the output voltage here to drive a speaker, right, the speaker is supposed to produce the same sound as you use to stimulate this sort of the ear. So I will skip this sort of a dynamic range calculation. Okay, that's too much engineering. The bottom line here is this is the detectable threshold. Tells us that at the 500 hertz we can detect 60 dB SPL, and at the higher frequency such as 2 kilohertz we can go down to 35 dB SPL. But to show you this works right is I have 3 sound clips. One is the original sound that I played, the Beethoven III. Okay, I played to this ear. Okay, so you can see the sound quality here. Right, so this is the original sound. So now this is the sound, the same music. I tune down the volume, okay, down to a normal conversation level, okay. As you expect, right, I should be able to detect the sound, but the signal to noise ratio is quite poor. Right? So you can hear the sound, okay? But because you are so close to the noise level, okay, you get a enhanced noise perception from the background. So the last thing is, what will happen if I cranking up the level? You should hear the sound, but the sound quality gets better, right, relative to the noise level. And this is what you should, this is what you should expect. Now you hear the noise level on the backside because you always have electronic noise or environment coupled noise, but the signal to noise ratio is much improved. Okay, so I see I'm over 5 minutes, but let me finish within the next 30 seconds. Let me draw the conclusion, right? So the microsystem technology developed to achieve basically 2 examples that I show you here today. Is wireless, batteryless, implantable blood pressure sensors for real-time genetically engineered mice monitoring. Second example, right, is the middle ear acoustic sensor for human fully implantable cochlear prosthesis. But to realize such a sophisticated microsystem requires 3 things. Now, one is conventional machining and the molding technique that typically has, a resolution on a sub-millimeter. That's what I constantly tell my graduate students, right? You can't really write a paper on this conventional molding technique, but don't neglect it because this is what you need to do in order to get the whole system packaged together to go to the next level. Nobody's going to do this for you. You are the only one, right? And the MEMS fabrication that has micron level resolution, and the CMOS technology, microelectronics technology, right? It's also this micron level resolution or sub-micron resolution. So it tells you that, right? To do this, you actually need to have the skill and the tools that cross quite a range of resolution. And optimum design, right? Cross biological system, right? Device circuits and the packaging becomes very critical for a successful implementation. You just cannot afford making mistake at any one of those stages because single mistake, right? At the device level, it wouldn't work. At the package level, it wouldn't work either. And so the implantable blood pressure sensing technology, right, is not only important for advanced biological research, but I believe it's also can make an impact for future healthcare system to provide early warning detection, for human emergency, right, events. And the MEMS accelerometer, as I demonstrated the last 15 minutes or so, right, can be used as an implantable middle ear microphone, right, enable us to realize future fully implantable cochlear prosthesis. And at the end, right, I gotta thank my research group members, right. I'm very fortunate to have a group of extremely bright and talented graduate students who conduct a lot of work that I talk about here today. I can't do all of this. As a matter of fact, I shouldn't be doing this because I have done my Ph.D. already. So, Pankang, who just finished the Ph.D., did a lot of work on the blood pressure sensor. Natapun, Suster, Zimmerman, and Mark Zorcher, all contribute different angles, right, for the slides that I talk about it. And my research collaborator, Professor Wenko from EECS, and a number of collaborators from Case Western Medical School. And of course, our National Science Foundation and National Institutes of Health to pay for what we do. Okay?
All right, thank you.
Sure. So any questions? It is a lot of challenge to position the sensors on top of the die. But from my own experience back, from my graduate school study, I deal with those sort of modules on the board, right? One thing is that, the gap between the bond tabs is very important. Okay, if you position the edge of the die to the edge, the edge of the MEMS sensors closer to the edge of the electronics, if the distance is too short, in particular you have the sensor on top of IC, you may not be able to do the good wire bonding. Or even if you wire bond it, you have so much stress it can easily, pop back up.
Does the IC design include an open area of field outside? Is that what the MEMS chip is sitting on top of?
Directly sits on your FET
on top
device.
of the circuits.
Yeah.
Okay, so it doesn't have to be planar.
Yeah, even if it's not planar, as long as you can glue it.
And so there's some sort, yeah, a glue or epoxy or something.
Yeah. You have to have some adhesive material to attach to. It's not just dangled right by. It's not held by the bond wire. There's a layer either underneath the die or positioned around the corners.
Other questions?
I was curious for your implantable blood pressure cuff. Were there any supports for electronics, like with the tissue? It's like a big mass swinging. I'm just curious, like the mouse moving around, you know, if there was any.
Oh yeah, I mean,
visibility
if you look at the implant picture, underneath the artery there is a tissue, but what's between the tissue and the artery is that substrate containing the MEMS IC modules and also containing the RF harmonic coil and other discrete components. On top of it, it is another piece, sort of flat silicone material, right, capped on top, with a thin stainless steel sheet, sort of encapsulated in the top cap to isolate the coupling.
Yeah, I was just curious, is there anything like holding all the electronics?